piece of paper doesn't automatically include the title or the date and things like that. So I went back and looked at it, and I was like, what would it? Anyway, I try to make it so it's easy to see what class and what time it is if you want to ever download or print those or for any purpose. Store them on your computer, then easier to see what it's for. So. Well, today we plan to describe talk about describing data some more, focusing more on the spread and variability, look a little bit at the R statistical program, how to get it, how to download it, how to get it started. We'll do more with that on Monday. Right? The homework that's due on the Wednesday has some to do with that. You can do actually a lot of the computing with that. For a smaller data set, it has to just do something a little bit by hand. But you can check that on the computer. I think it's a useful tool once you get used to starting it and importing a data set and a set of commands. It's pretty flexible. It'll be kind of the same pattern to get going. So after a few trials to get it to work, it will be a useful tool that we can use throughout. This article on Down syndrome, I'm just handing out now. We'll talk about it on Monday. Kind of get you interested in your impressions of it, what you think about it. I think it's interesting because it uses some descriptive statistics. It talks about different types of studies, and talks about more of the history of learning within that some aspects of Down syndrome and research in general. But it's not just one study, but it's kind of taking evidence from a lot of different sources and trying to put it together for an understanding. So we've talked some about surveys and experiments, and then describing data in different ways, and this is kind of a neat, I think, an informative perspective of how something like that might fit together. So we'll just have a discussion, ask a few questions. So I encourage you to read it and think about what's interesting and how they learn, how they decide if things are true. So the homework's posted, and homework 1 solutions are posted. We will have a grader, a teaching assistant, for the class, mostly grading. So she has the homeworks now, and we'll be looking at them. So I don't have them right now, but as things get going, the plan is to be on schedule and get things back to you a little quickly, kind of promptly. But it's going to take a little while to get this initiated at the beginning. But homework solutions are posted if you want to look back at any particular questions. And we'll have plenty of time to talk about that once you get your homeworks back. So for the homework 2 that's posted, let me just show you a little bit on Canvas before we talk about a numerical example. So homework 2 is posted here. I changed this little title, so this one's posted. The homework 1 now says solutions, because the solutions are there. So there's the PDF or Windows, the version of the document that lists the problems on there. There's this R data. Those are the R data sets. So if you want to download that to your computer and put it someplace that you can find that file. Right? So generally, if you right-click, I think you can save that link as someplace and just save that R data set somewhere on your computer. There's also this thing called this R script. It's a set of commands that can be useful for executing things. Right? Particularly as we learn new commands and new things in the computing, I'll probably show you examples of doing something like that. Right? If you read along on those and save those would be guides to how to do different computing. And you could follow those examples throughout the term and for a project. Right? But that also, if you right-click on that, and I know I'm using the Windows machines, it might be slightly different for if you're working on a Mac or something. But if you save that, then you can save that R script file somewhere. Those are the 2 essential ones. These were the original data sets, a cholesterol validity for diet measurements, and some data from Professor McCabe in biology about bugs in streams. So you can save those and look at the original data sets, but it's all incorporated into the R data or the R script files. Right? So save those and you're good to go. And we'll talk about starting R and getting those things in with some examples today. But, so we were describing a data set. We've talked about a few things that we might look at. You might look at the graph of the values to look at just kind of the shape of the pattern of the values. You can kind of see something about the center where it is. You can see something about how spread out the values are, or do they cover a wide range or narrow. We looked at some quantitative summaries of center, particularly mean and median, as examples of those. And today we'll talk about more of the quantitative values of spread, and another graph called a box plot that's often useful for depicting the graph of the values. So the purpose of describing the data set is to be able to summarize what you have, say things that are you think will be characteristic of the phenomenon you're studying. What are the averages? How much spread is there? Right? Maybe compare groups, which one's higher or lower than the other one. Right? And so in terms of measuring spread of values, we have a bunch of values, generically x1, x2, x3, up to xn as our particular values. Right? And one basic measurement we can have, right, is simply the range. You can tell me the highest value and the lowest value. You tell me what they are, minimum and maximum, highest, maximum. The lowest is the minimum. And the difference between those two could be called a range. What's the span between those? And sometimes that would give you useful information. If you're looking at luxury homes that ranges, from 1 million to 10 million, you have a $9 million range. If you're looking at rental apartments and you're dealing with rents, or you're dealing with $500 to $2,000, it's a much smaller range. So the range can tell you a lot about the problem, but it is sensitive, right, that the range will be bigger if you have one observation that's really big, right? So if you have luxury homes and you happen to have one mansion that's $60 million, right, that's going to make that range look much bigger. Or if you happen to get in your sample one luxury, apartment that has 2 floors and 4 bedrooms and rents for $4,000, that's going to make the range much bigger, right? So the range is completely sensitive. Sensitive to the extremes, and it doesn't really tell you much about what's in the middle, right, of it, right, or what's away from the very extremes, right? So you could do things like take out the upper 5% and the lower 5%, take out the extremes and say what the range is that. That type of thing is called a trimmed range. Some computer programs will compute that as a standard summary, take out 5% or 10% from the extremes and tell you what's in the middle. Right? So if there were a couple mansions, but the rest was more regular, I guess you could say not quite as extreme, right? Then the trimmed range would be a lot shorter than the range, and you would get some idea that there's some big extreme values that are in there. Right? So this might be something like the 90th percentile and minus the 10th percentile. And that's less sensitive. And it gives you still an idea of how spread out things are. One standard measure that's come down is called the interquartile range. And so this one is taking the 75th percentile minus the 25th percentile. The 25th percentile is also called the third quartile, right? Kind of like quarters. The third quartile has 75% of the values numerically below it, added or below. And the 25th is called the first quartile. It has 25% below it. There's also a second quartile. What would be another name for the second quartile? Yeah.
50th percentile.
50th percentile or median is, right? So dividing things up in quarters, right? So this is even less sensitive than this trimmed range to to extremes, right? So it's the central 50% of your data. In a way, that's saying something that these values are very common. You have 50% of your data here is in the center, 25% is below, 25% is above. But still, you could compare, apartments in different sectors of a city and say, well, how does that range go? And if that range is bigger, there's more variability, right? There's more differences in the sample. Interquartile range sometimes is abbreviated IQR. And it's meant along with, median, first quartile, median, 75th percentile, and maximum, and maybe these 90th or 10th percentiles. If you know all those numbers for a set of data, you know a lot about its shape, right? What are typical values, right? And you understand what's going on with the sample or population pretty well. And these things really are comparative. If you have two different data sets or two different groups, and one has more spread, the values are more spread out. One other measurement we will use, and it's common, is standard deviation. It's abbreviated as S. S, the standard deviation, is the square root of the variance. So S is the square root of the variance, which is S squared. The variance is S squared. And S squared is calculated in a few steps. So S squared is calculated by taking our values I minus their averages. So we take these deviations of a point from the mean. Some of those are positive, some of those are negative. But we're going to square them all, make them all positive. So we're going to take these squared deviations. We're going to add it up for all of our data points. So that's the summation sign. Some data sets have more data values than others. So we're going to divide it by something, kind of like averaging. We use n minus 1 as the standard instead of n. It's about the same. Value, particularly if n is large. Dividing by 1,000 versus 999 doesn't make much difference. There's there's some rationale and some statistical theory that we'll see eventually that people use that. And that's called our sample variance, right? So let's look at one example of computing that. And in this course, you don't have to do too much with the formulas. The book does use the formulas, so seeing it and putting the symbols in with numbers is good to do. We won't do a lot of mathematical expressions to manipulate that. Have I started my... we have a PowerPoint. Is that going? Yes?
In the parentheses, it's the x initial minus the average of x?
Yes. So this x, this index I, is going to go through all of our data points. So our data points, x1, x2, up to xn, this is saying we're going to call those xi, and then we're going to have this index go I, 1, 2, up to n, and so that it's the kind of generic index. And it says go through it and add it up. And this example here, so we kind of talked about these things. Here's a numerical example with the 5 points that we used for the average before. Right? So if we had points 12, 8, 5, 5, and 25, these are our points under the xi column. This would be point x1, point x2, x3, right, x4, and x5 here. And the summation notation, right, taking x1 plus x2 plus x3 plus x4 plus x5, in this case is this summation, and those things would add up to 55. So our sample average divided by our 5, and we get x bar, right, as 11. Right? And so our formula for the spread takes each of these values and subtract the average to get its different distance to the average. Right? So 12 minus 11 is 1, and 8 minus 11 is -3, and so on. These deviations actually add up to 0. Right? Then you square them, right? Make all the numbers positive. You get 1, 9, 36, 36, and 14 squared is 196. And the summation, the sum this thing here, the sum of xi minus x bar squared is that, I goes from 1 up to 5 for our 5 observations. In there is 278, and then we divide it by n minus 1. Right? N minus 1 is 5 minus 1, in this case, or 4. So we get a variance of 96.5. Right? So that's just that computation of what that variance is. Right? Now, standard deviation, we just take the square root of that. Right? Square root, do all of that, and then take the square root of it, and we get 8.34 as our standard deviation. The square rooting is important because if the original things were in dollars, you know, a $10 check, $8 check, $5 check, maybe these are tip amounts, right, of dollars, and we take deviations and then square them, it's in dollars squared. Nobody's going to pay you in dollars squared. It's not something like Bitcoin where it's imaginary and you can still pay for it. Stuff with it. But it's dollars squared. So we take the square root and it goes back to the original measurement, back to dollars. Right? So that's kind of the mechanics of the computation. Are there any questions about the mechanics of it? There's one other computational formula where you take the average of the x's squared and the sum of the xi squared. So the book might, I believe, does express that as a computational formula, but that's just another way of computing the same. I kind of like this one because the difference of xi minus x bar expresses how far away points are. It expresses that distance there. For the most part, we're going to do it on the computer anyway for larger data sets. So if you changed one observation, here's this one change. Now this one's 55 instead of 25. Now the average is higher. Now x bar is 85 over 5 is 17. That's changed. The deviations of the points from the new average have changed. Right? Generally become more extreme. And then if you square those, you get these big numbers. And now our summation, this again is our summation of xi minus x bar squared over those 5 points. Now is 1838, before is 278. Right, we divide by 5 minus 1, n minus 1. And now this square is quite a bit bigger. And we take the square root of that to get the standard deviation, and it's almost 3 times as big. So that 1 point changing kind of blows up the standard deviation because it's so far away from the others that this measure of spread and variability just gets inflated a lot. So it, like the average, it is sensitive to one extreme value. Right? If I really had to describe a data set, I wouldn't report just one thing, standard deviation, proportional rates. I'd want to show a graph and give different versions of the numbers. Right? That's really communicating more. Sometimes you don't have that much space or time to present all that, but it's more effective. So any questions now? So let's look at how this goes in some summaries for some of the survey data. Make this a little bigger here. So this is what's called a box plot of cigarettes per day. This vertical axis is cigarettes per day. In that Gallup survey, there were 1,379 individuals, 1,326. They were all identified as smokers. Said how many cigarettes per day. The standard deviation, if you calculated for these data, turned out to be 10.5. The variance was 110, but the relevant one for thinking about cigarettes is at 10.5. Right. Now, larger values of standard deviation indicates more spread, right? So if you took, say, people who had only smoked for 1 year, I don't think that they would have values up at 50, 60, 70, like those others. They'd be narrower in their range, or you get a standard deviation that'd be smaller for people that had not developed such a big habit, right? And the average was, I don't know if the average was on here. In any case, we'll figure that out in a minute. What this box plot does is another picture of the value. Right? And it's kind of tied into some of these percentiles. Right? So the middle value is the median in here. That's at the 50th percentile. And that value here looks like about 10. Right? So 50% of the sample is saying 10 or less, or maybe 10 or more. 10 is right there in the middle. There's probably a wide band of people saying 10 and about 50, somewhere in the middle, so 50th percentile, you sort of thing. Then in this box, the lower one is the first quartile, or 25th percentile, and the third quartile. So for these data, the first quartile is 5, and this one is 20. Right? And so this is the interquartile range, is 15. 15 cigarettes is the distance. So that gives the central 50%. So 50% of the subjects responding, of that 1,300 some, right, is between 5 and 20. Right. And what else is in here is we draw lines down to the points or indicate the larger points in that. These are the lower 25% are in this range from 1 to 5. And then the upper 25% are in that range. Right? And there's slight variations in the rules. This one, we don't have to go very far down to 0 or 1, and that's the limit there. So that line goes all the way down to the lowest value. Right? Going up this way, we draw a line from the third quartile up to 1.5 times the interquartile range. So the third quartile was 20, and the interquartile range was a distance of 15, so this is 22.5. So 22.5 is actually probably a little bit above this line, but we don't actually have a point at 22.5. 40, there's some clumping up there, 40, 50, 60. Right? So this line's going up to about 40. Right? And then anything that's beyond that, that's really in the data, gets illustrated by a point. Right? So you see kind of some of these extreme points as well. These things are out here are marked as potential outliers. So they're potentially extreme, potentially beyond what the usual variation for this data set. Right? But it gives you a lot of information right away, right, about the spread. These things are really useful, I think, when you're comparing groups, and you can put 2 blocks plot side by side, like we'll do in just a moment, to do that. But it captures both something about the center, certainly the median there, and the spread, outlying points. Would this data be skewed to the left or skewed to the right? Which side has the long tail? Left. Well, left is this one. It's kind of clumped up here at the left, right? 25% is in this narrow interval. So if I talk about the tail being long, and in terms of extreme values sticking out, then I would say the right. So going the other way. Yes.
Can you repeat why you're adding 1.5?
Why is it that formula, this type of thing, to draw those lines? That's how it's been described, right? In the literature, kind of as a descriptive tool. Right? So there is some underlying thing about distributions that are slightly non-normal. What percent is a certain percent, about 5% of the points, that tend to be above one or the other in things. So we will look at some calculations with normal bell-shaped distributions to show that it doesn't identify very many points, a very small percentage that's out there. But that's how it's kind of come down as a
Is 1.5 like a constant? Like
yeah, a constant that's been set up for kind of, yeah.
Okay.
Pretty much, most software things do it. They could do a little bit of variation in how they draw this line and do a few other things, but it's something generally quite similar to that. 1.5 is described in most of the books. It's the R package that made this plot is doing 1.5. We'll get a little bit more explanation of that when we look at actually computing areas under probability curves. Right? So it's useful when it's comparative. Right? So here's females and males. A separate box plot is computed separately for each group. And these are the number of cigarettes per day on that. Okay? So how do these two groups compare in terms of cigarettes per day? And when looking at graphs, you can pick up on any interesting feature. There's a lot of different answers that you could come up with. Right? And they're all valid for description and saying what is apparent there. So anything striking about comparing females versus males?
It's like kind of like the whole like dark side. Is that like a standard deviation?
This is median.
Median.
This is the 50th percentile. So 50% of the women smoke 10 or fewer, 50% would be classified as 10 or more. But for the males,
It's like closer to 60.
it's closer to 60, right? It's a little bit higher. Right? So in terms of if median is what you mean by typical, then typical males are smoking more. They both have some outliers that are up high. They both have short tails, so probably the distributions in terms of being kind of skewed with the longer right tail is pretty similar. The 75th percentile up here is actually the same at 20. A lot of people, regular smokers, report 20, so that's a pretty common response to both. Right? But it looks like it's shifted a little bit with males smoking a little bit more. Here's a comparison based on age group, and I could have labeled this better. So these are the people that are less than 40 years old. Right? And these are the individuals that are greater than 40 years old. And this axis is the number of cigarettes per day. In R, you can add labels to that, so if I could prove that graph, I'd add a label as to what's on that axis. How does the amount of smoking per day compare by age group?
The older you get, the less likely you are to smoke.
Well, so these are the older ones, right?
Oh, that's older.
Yeah, this is older, yeah. These are
If you're
older.
older, then you're more likely to.
Yeah, you're more likely, the amount that you're smoking on this axis is typically higher. Right? So the longer people are smoking, it's addictive, they're tending, the message of this is, an interpretation is that they tend to continue smoking larger. So there's a lot of important things that could come out of this, well, right, besides the shift up to being higher. Both groups have a lot that are smoking very, very little. So the physical process of addiction, if you're only smoking that little tiny amount, maybe it's not that strong. Both groups also have individuals who are smoking a lot, so the physical response might be quite strong. So kind of interesting to do that comparison. But any questions about? In R, in the computing, we can get exact values of the different percentiles and things from this graph. It's like to kind of eyeball it.
What is true and false referring to?
True and false, I told it to find groups out of my subset. And one group I asked, was it less than 40, were they younger? And so it was true that they were less than 40. And so it divided that as a group.
Mm-hmm.
And I could change the labels if I made it a little bit better to say less than 40 versus bigger than 40. So.
That makes more sense.
Yeah, this one, it automatically got labels because there was a variable that says male, female. And if I created another variable that said younger, older, then it would show up back in there as well. So use and interpretation, this is quite a bit of information. But the main idea of using that S, that standard deviation, right? So it is comparative. So if a data set has a bigger standard deviation, its values are just more spread out than the other one. Or maybe it has one or two big outliers that boost up the standard deviation and cause it to be bigger. But there's a few different calculation rules. But the usage that I'd like to do for us is that most of the time, a significant portion of your observations, of your actual values, will be within plus or minus one standard deviation of the average. So what that ends up meaning, right, if we go back to our picture, so the use of S, so comparative is always a good thing. A good way to use that, comparing groups, which one has more spread. If the histogram, rough picture is kind of symmetric like this, then X bar is going to be somewhere in the median to be somewhere near the middle. And if you go X bar plus a standard deviation on this axis, this direction, to minus, it's going to incorporate a lot of the observations. More than 56%, but. And if you go plus or minus a couple standard deviations, it can be 90, 95, 98, 99%, so it can incorporate a lot of the observations. So if you know mean and standard deviation, it tells you a lot about what the individual values were if it's symmetric like that. The rule, though, kind of breaks down if the data are kind of skewed, right? Because then the average is going to be over here, and you might go x bar minus 1 here and x bar plus 1 over here, but you can't go too far because of the skewness. And that those big values out there, probably are more standard deviations away. It still gives you some idea of where the values are, but it's always important to know the shape, right? For understanding data. So in one of these variables on this next picture, these are the number of cigarettes per day. The histogram, so it's the black lines that are light underneath that, right? And it's kind of clumpy with some 60s and 70s and a lot of bigger values down there. The average, x bar up here, was 13.8, is that red line. And the standard deviation was 10.5. So if you go down 1 standard deviation, you're about 3.3. And if you go up 1 standard deviation, you're at 24.3. Well, a lot of the observations about the values that people report are between 3 and 24. That's most of the data set. There's a few that are less. Even if you go up 2 standard deviations to 33, that doesn't quite cover that upper tail because of the shape. But still knowing x bar, the standard deviation, could be useful for some things that you'd want to do. Okay. But any questions about it? So we're going to do a little bit abbreviated on this next example. The next example for the education data set in California. One thing that each school gets measured on in California is called the Academic Performance Index. It's based on standardized testing of the students, and there's elementary questions, and middle school and high school questions. And there's goals for achievement. And a data set that would study this would actually have a lot of different variables in it. Everything ranging for things describing the school, its name and everything, scores, percents of students taking it, things about students, class sizes, things about the parents, and so on. And so there's that and probably 100 other variables that the state keeps track of at these. And data sets usually are, for our analysis, will be arranged in rows and columns, with variables going across the columns, and then different rows for different high schools or elementary different schools, and so on. And here's some of the examples. Sometimes the values are missing, so on. So for like Alameda City Unified School, here's one of the schools. In their 96% were tested. Their API, the performance index of 2000, was 731. They have things like 14% of the students are getting free and reduced price meals, 16% are English language learners, and so on. And you can describe, I'm not going to focus on this, but you can describe the categories. There's 70% of the data set's elementary, 16% is middle school, and 10% is high school. And you can look at a number of these variables. So I thought these were just 3 different interesting variables. The contrast here on the left is the entire population. And on the right is just a sample of 200. Right? And it's just an artificially generated sample of 200, and they just took a simple random sample on the computer. And the graphs look quite similar. Right? This is a graph of the percent of students by school who are English language learners across the 6,000 schools. Okay. This is the percent of students who are getting free and reduced price meals. And this is the academic API score in 2000 across those. Right? What are some significant features of some of these variables? Are all schools the same? No. Right. How are schools variable? How are they different from one another?
Well, from the graphs,
the entire population and the samples, like they're pretty much like the same curve.
Yeah, yeah. So the sample's pretty representative of the population. A little bit variability here and there, but they're pretty similar, yeah. If you just focus on these, the whole population. Some distributions are skewed to the right, and there's a whole bunch of schools that have less than 20% English language learners, but others have a lot more. A lot of diversity within schools. I wouldn't have expected it, but the percent getting free and reduced price meals is pretty uniform. I would have guessed it would be more extreme, more separated poverty, but you know, it's been pretty even. The test scores are more bell-shaped, more symmetric. These would be well described by X bar plus or minus a couple standard deviations for kind of the ranges there. A lot of testing things where you're kind of taking averages or composites end up kind of being a little more bell-shaped, so we'll think about that some more. But if you take the graphs by type of school, high school, middle, and elementary, and wanted to compare them, you could make graphs. But you can also look at measures of mean, median, standard deviation, interquartile range. If you need to do a report comparing how schools are doing at the different levels, you might incorporate different graphs and different summary statistics. Of these three types of schools, which type of school seems to be faring better than the others, or worse? Yeah.
The high school ones are kind of faring the best.
Think so? So.
Because a lot more of the higher values are.
Yeah, so there's kind of a cluster up here, right? A little bit higher, right? So that is true, that impression. It's more skewed to the left. There's this lower tail bent down. What about the ranges on the axis?
Yeah, say the elementary school is doing the best.
So elementary school is doing the best. So what feature are you picking up on the elementary schools doing well?
It seems that more students are doing well or in the middle range than a lot of students doing well, and other students just.
Yeah, so these graphs aren't made as good as they maybe could be made, right? So if I made these all go from 300 to 1,000, or maybe 0 to 1,000, and put them all on the same scale, it might be a little more pronounced. But there are a bunch of schools that are up above 800 here, a few in the middle schools, but not any in the high schools that are above that 800. So assuming that they all have the same kind of meaning of the scale. The test questions are probably adapted to the level of students. You know, you're not asking the same questions in the high school as the elementary, so it's kind of the relative thing. If you look at the averages, right, the mean for high schools is 605, 654 middle, 666 for elementary. And the medians kind of track that same pattern, but are a little bit different. So there's some students, you know, schools at every level, some are doing really well, and there's some that are doing quite poorly. So the variability in the ranges is quite important to know about. Standard deviations and interquartile ranges, the elementaries, it's hard to tell from the graphs exactly. But these are going from, you know, the 400 to 1,000 with spread at both ends. These are going from 300 to 18, but a lot of it's, you know, 400 to 800. So that spread is a little bit less. It's a little tricky sometimes to go directly from the graphs to some of these numerical things, but they kind of support each other if you needed to write a story about it. What you really want to know is, you know, what are the characteristics of the schools in terms of all those other variables, in terms of are they doing well or doing particularly good, and how are these different things related to one another, probably. But any questions about? So I want to look at one other small data set so we can actually look at numbers and talk about how things are influenced and get at this idea, average and variability and depicting it, right? So this happens to be a baseball example, right? Two historic baseball players are Hank Aaron and Babe Ruth, and these are the years that they played. Right? And the thing that's reported here is the number of home runs they hit per season, and these are in order of the seasons they played, so 1954, 1955, etc. to 1976. And so these are the actual values. Not quite the equal numbers for each one, but still but similar. And so if you're given these data sets and wanted to compare, what's something that you notice about these distributions? How do they compare in some way? Yeah.
Kind of like Hank Aaron's is kind of like more kind of like moved towards like the 30, 40 kind of range.
Yeah. So if you look through here, look at all this, like all these 30s and 40s. That looks pretty consistent, right? Babe Ruth, 29, 54, 35. You know, it's kind of more variable. Right? So that's kind of an interesting aspect of the pattern. Anything else? How do they do at the beginning and the end? Oh, you go ahead.
Babe Ruth just has a bigger range, like his highest is 60, lowest is 0. The other guy, I think the highest was 47, and lowest is 13.
Yeah, or 10 down here, yeah. So yeah, so looking at the numerically, the ranges is more narrow in there, right? Does anyone know why Babe Ruth had these small numbers at the beginning? He was playing for Boston, and he was a pitcher, right? So he was pitching, not necessarily playing every game, and his role wasn't to be at the start of the batting lineup and get more attempts and that, right? So, but he was traded to New York, and Boston didn't win the World Series for, I don't know, 100 years or something like that. But in any case, you know, there's a little bit of background there. So if we look at these in a slightly different way, so this is the stem and leaf plots of these same numbers. Now we've lost the time order by putting it this way. That's one thing you lose. Right? The time order is kind of interesting. Both of them kind of have an upswing as they're starting their careers, and then a downswing as they're ending their careers. That's part of a time series that you don't really see. So these are the two stem plots, right? So there's the 10s, 20s, 30s, 40s for these, and similar for Ruth. Right? Does this help show anything that you've talked about? We talked about the ranges, right, and the variability, right? Does this kind of make it clear, right, that Babe Ruth had more variability? He had this beginning career, but even if you took out those first few years, there still seems to be a little bit more variability. Right? And if you add more people in, these box plots can be really useful for comparisons, I think. Right? I've used these in numerous examples for looking at subgroups, time frames, different geographical areas. And so these are 6 players. There's Hank Aaron and Babe Ruth in there. Roger Maris was another historic player. And so at the time that I was putting these together, 10 years ago or more, Frank Gifford Jr. and Mark McGwire and Sammy Sosa were big hitters, big players in the major leagues of baseball. McGwire is one of those now that's no longer included in their record books because of drug use, steroids, and things like that. But I could update this probably every 10 years or so. I could probably update this. Right? And so these are the home runs per season for these 6 players. By looking at this side-by-side plot, what summaries can you? Yes.
There's 2 medians that are like kind of outliers in a way because they're a lot less than the other ones.
Yeah, the Griffey and Maris are kind of lower. These medians, the dark black lines, are a little bit more consistent. Yeah, so kind of 2 groups maybe. Does anybody have an outlier? And Roger Maris had this one. This is when he beat Babe Ruth's home run record of 60. That was the biggest one. He got 61, which was really a surprise, right, because of where he'd been before. So the sports commentators probably love that. Others have more variability maybe, like Babe Ruth had this huge variability and Sammy Sosa had some. And others, like Hank Aaron, were pretty consistent. So that comes through. So when any data analysis like this, you can look at other variables too. So this is not everybody gets the same number of chances to hit a home run. The pitchers, for example, didn't play as much. Some players get injured, they miss part of the season. Players that are on teams that are really successful, they can go through their lineup and get more chances. And teams that are not doing so well, they're out quickly and they don't get as many chances, right? So there's a lot of variability in the number of at-bats. So these are the number of at-bats per year. And there's some variability within players, but also across time. And there's a relationship, right? The number of home runs that you're getting seems to go up with the number of attempts. But it's not a perfect relationship, but it's, you know, it's a positive one. So to adjust for that, you could do something like take a rate, right? You could take the number of home runs divided by the home run rate for players, right? And if you do that, you know, it's about 4%, 6%, 8% per year, or per attempt of getting that. Sometimes it's convenient to rescale things, so it's a little easier to talk about. So if you multiply that by 100, you get this graph over here. It looks the same, but now it's, you know, 6, 8, 10, just integer numbers. And this would be the number of home runs per 100 attempts. Given that they get 300, 400, 500 attempts, that's kind of maybe a useful summary. Right? So it's a different ordering of the players, slightly different impression, right? You change the variables, you get a different impression. And the graphs can kind of help bring some of that. Any particular comments on these rates? We had kind of a 2 standing out on the low end before. Right? Now we kind of have 2 standing out on kind of a higher end, right? Babe Ruth and Mark McGwire. Now McGwire's no longer in the record books because of the drug use, but Babe Ruth kind of is standing above those. His 50th percentile is above the 75th for the others. And some are more, Roger Maris, some of these are more consistent. So you just get another take on it, something else that might be an interesting insight that adjusts for some variable by just taking this ratio. Right? And so a combination of graphs and numbers and things like that can tell interesting stories. Just 2 brief notes. Well, we can do more with transformations, and we'll do more with that later. Data over time, like that time, like the home run rates, or weather over time, or economic data, or people's health over time. Really, there's a time series structure under it. We won't do much with that in this course, right? There'll be more advanced statistical methods, but often it's important to note that just an average or standard deviation doesn't capture that whole time dimension, and it's important to think about that. So in economics, there's time series models, there's longitudinal models of health, of people's growth, over time, and there's special methods for that that would be probably covered in a course after this one. Let's look a little bit at the computing, okay? So again, we'll do more computing. How much time do we have? So we have a little bit of time to go over a few things, right? That later. So as described in the handout, to get going in R, you want to download R onto your computer. It's also available on these computers and some of the labs and maybe the libraries. I'm not totally sure exactly where it is now, but it's supposed to be generally available. So CRAN is this comprehensive R archive network. And so up here is a download, Linux, Mac, or Windows. And you click on one of those and just this base system, you can click on and it gives you a thing to download. If you click on that, it will download it. Oh, I didn't want that. In any case, it's going to do that, download. And once it's there, we'll look at it, show all the downloads. So I had done this before, right? And once it's downloaded, if you click on it, right? Do you want to modify your computer? Okay. Right. Let me cancel this other one and go back to this thing. What language do you want? Do you agree to the terms? And a few other clicks. Standard locations for everything is fine. And then it will install. Right. Takes a couple minutes to download, a couple minutes to go through that process, and then R is installed, and you should have a little exit setup, right? You would have a little R icon on there. The next step would be to download RStudio. So if you just type RStudio, there's the website for it. And it asks you whether you want to download it. Right? You can click on that to download it. You can download the free version. Right? There's these corporate ones that are fancier. And there's different things for different types of computers. Again, you click on that, it's going to save it to your computer, and then you run that program and it will install. And what you get out of that is an RStudio icon, this little R here. If for some reason those things don't show up on your desktop, you can go under, just search and type in R, like there's RStudio, shows up right there, and you could start it from that. But these things are designed to allow you to put these icons on there. So from that icon, you can just click on it, double click on it, come on, there you go. And it will start up. And mine's going to start with a few things already in there. So let me kind of clear out one of these things. It'll start out with this. This console is where commands get executed. Right? You want it 5 times 3, and it'll give you 15. Right? If you want to enter some data, right, I'll call it Y. You can call it whatever you want. This is a little symbol for assignment, and that C means concatenate, put some numbers together. So we had 10, 12, 15, 13, and 14. I've created an object called Y. Right? Y, if I just type return, shows me those values. I can multiply everything in Y by 3, and it's going to multiply everything by 3. Up here in this environment, it shows me I have an object called Y. Now, if this is special to me and I want to save it, I'm going to want to put it someplace, right? So I'm going to want to work, it says files down here will help me find something. And let's see, how can I go to a working directory? Okay, that's where it is. I don't want to be there. Okay, now I can see up here what's going on. I can go back to St. Mike's Net, and then I want to go up. Okay. Home, doesn't know where my home is? No, it doesn't. So let's see. What I'm going to do, another way of doing that is you can set a working directory up here and choose a directory. So I'm going to do it that way, because then I can choose my computer, and I can choose my 140 class here, and the lecture for today. A lot of stuff to click through. Is it in there? Maybe right there. Is where it is. I'm going to go to there. Right? So now I see some stuff. Right? So if I want to save this data set, I can say save.image is what it's called. And data Y, and it's an R data set. Right? So I'm going to save that. And is this, where did that go? Data, set this thing as my working directory. And now within R, you can kind of just use your arrow keys to click up and down. So let me save that. And I think that's where why isn't it saving there? Is it, where are you? No, that was a previous lecture. Did that save it there? No, that's not my data there. So let's see. I know what happened. It just didn't refresh. Is that it? Reload that. Oh, I went back to that. Okay, this is getting frustrating. Okay, so I'm going to set working directory. I'm going to choose a directory. And okay, lecture 7, I don't want lecture 7. I want, it could be lecture 7, I guess. Okay. So yes, okay, it's there. It did save it, it just took a while to figure out that it actually was saved. So what you will do, instead of that little bit of frustration there, right, is if you have this RScript file, I just clicked on it and it opened up here. This RScript file has a series of commands that are in there, and here's some little directions. And so this is a place that saves commands that then you can run. One way to do that is to just highlight it. So I looked on my shelf and I had clumps of books, and I counted the number of books in certain clumps. Not everything. And so you can take that command, you can copy it and paste it down in here, and it will run. Or if you're sitting there, you can press run, right, and it will execute that command. If I press, I'm sitting here on the link, how many clumps were there? There were 7 clumps. what's the average? These are commands, let's sort them, right? You can also, there's also an interquartile range command, IQR. And so you can type things there. If you want to save it, you can put it up there and then save this thing. So if I type something new in here, like interquartile range, right, it's changed. I can click this little save button, and I've saved my thing here. Right? File. Or I think file, save as, we'll save it as something. So it will save that RScript file and you can give it a new name. But anyway, you can save your commands. Right? I talked a little bit about saving. Right? Now to get out of R, you can just type the Q button for quit. Right? So if I run that, it's going to quit. It's going to ask me if I want to save that thing, but no, not really. I've already saved stuff. And now it's gone. If I go back up here, this is where I was working. I was working in number 7 here. And then I had the data that we're going to look at here is an R data set. If I just actually open that with RStudio, it will open, and there's a little bit more work that I had done before, so it loads in all the data sets. So if you save the R data file and that R script, and after you've installed those, you can just open it and boom, the things are there. So this environment says I did this other data set, countries. How did I get that country? Well, this countries data set is sitting here. Where is it sitting? It's sitting right there. It's a data set on a bunch of countries. Here are the countries in alphabetical order. And it has a bunch of variables, land area, population density, etc. This is a particular data set. It's a comma-separated file, CSV file in Excel. That's a particularly easy one to get into R. Right? And so there's a little command to write it in. So it doesn't see it. Does it see it there? No, it doesn't see it there. So let me move to, there it is. All right. Again, I'm going to make sure I can set my working directory. I'm going to set that location there as the working directory. Now when I read it in, let me get this thing ready here. Now it loaded it in. Right, so that countries is there. It shows up here. 217. I clicked on it, so it can open there, kind of like a spreadsheet. You can't edit things right there, but you can look at them. If you click it, it will go down and tell you the different variables that are in there. Right? There's a few other ways you can look at the variable names. These are the different variables that are there. You can look at the first 5 rows of there to kind of get an idea of what's there. Tails, let's at the last one. It looks like there's a couple blank rows that are there. Right? That in that Excel file, there might be a couple extra rows that it thinks has data. You might want to get rid of those. And to make graphs, you can reference one of the variables, like make a histogram. Now, this is land area. This is an extremely skewed variable, right? You have things like Russia and China and the United States, and a few countries in Africa that are just enormous in comparison. Maybe Germany is also large, right? In comparison to a lot of these island countries or other small countries that are there. If you take the log of it, it actually makes it a little more symmetric, and so you can transform it that way. Box plots can be done. You can add labels to that, so like the name, if this is, there's different options that we'll explore to make things. You can make this a nice little, make it horizontal so it fits on the page there a little bit better. You can add titles and things like that. Let's look at the smallest countries. Right? So if you sort the land areas, it's going to put them from smallest to biggest. Right? There's a way to take the first 10, and this is a little command for taking the first 10 of them. So the smallest ones have tiny land area in comparison to things. Which are those? There's some missing values, so there's a little extra there beyond what we've kind of been introduced to. But the smallest ones, if you want to look at them, Aruba, Bermuda, Channel Islands, Liechtenstein, Macau, were some of the smallest islands countries there. If I want to do things to continue looking, instead of doing that little $sign to refer to the variables, right, I can attach that countries as an object And so, that's okay. And so it knows now to look for these variable names. So one of them was death rate. I can look at the death rate across countries. Some are, this is per 1,000 people, some are quite small, some are higher. You can summarize the death rate, minimum, first quartile, median, mean. It doesn't give the standard deviation in there, and never understood why they didn't put that one in there too. But you can get that. There happen to be some missing values, so I need to tell it to drop out the missing cases. Right? I can make stem and leaf plots. Here's a little stem plot. This can be moved up here a little bit. This is the stem plot of the death rates and so on. If I wanted to keep this graph, under export, I can copy it to a clipboard, right? And then I could paste that into a Word file or something if I wanted to keep that. For your homework, you won't have to keep all the graphs and all the output. I don't want you to print a 20-page thing. A balance between some key graphs and some summaries of what is coming out of this will be fine as we go through it. Right? In the end, I can save, now that I've read in that data, if I save it, then it's there and I come back to it. So the process for the homework is if you download that R data file and download the R script file, right, install R in RStudio, and then open those two files, the R data file in RStudio. RStudio should pop up with the data in there. You can double click on that R script file, that'll pop in. So then you have your data and your commands that you need to do to walk through most of the homework. And at this beginning part, the commands kind of guide you through things that you might do. You're welcome to try a little bit more and experiment, look at other variables, but it's going to guide you through those first things. Later, you'll be asked to just describe data, and you'll repeat some of those same commands with new variables. And by the end, when it comes time to do a project, you've had all this experience of these commands and things that you can pick and choose more what you think is appropriate. So we'll go over a little more descriptive on Monday, kind of go back through some of this R stuff, get a little more praxis, maybe have you do some of the work and figure out how it goes on there to see what type of questions are arranging. So if you look at it a little bit over the weekend, we can have some more, kind of figure out what the trouble spots are in terms of getting this work. All right, thank you. Thank you. Have a good one. See you. Thanks. See you.
Thank you. Have a good weekend.
Thank you. You too.
Thank you.